Okay, guys, let's begin. Yeah, yesterday I did some examples on the ETT, the extremal types theorem, and I also showed you how to choose the constants a(n) and bn in the ETT. Then I started talking about this thing here. And can you see this, guys? Because the ETT is a mathematical result, and checking which of the three limits is attained involves checking mathematical conditions. So a practitioner who works in biology or agriculture or environmental sciences may not have the knowledge to check the conditions 1, 2, or 3. So in that case, it is convenient if there is a mathematical form that combines the three limiting distributions, the Gumpel, the Frechet, and the Weibull, into one formula. So the question was, can it be done? I mean, can you find a mathematical form which combines the three limits into one? The answer is yes. And the formula that combines the three into one is known as the generalized extreme value distribution, or short GEV distribution, right? So the GEV distribution combines the three limiting distributions into one formula, right? And then I showed you the formula for, so this is part of what I talked about yesterday. So this is the formula. This is the formula that combines the three limits into one, right? There are three parameters in this formula. The mu parameter, which is the location, sigma is the scale parameter, and psi is the shape parameter. And the domain of this distribution is defined by this condition here, right? Then I showed you how to work out the domain for the three cases. So starting with the case, if psi is 0, then the domain can be worked out to be this, right? This is the domain of X when psi is positive. Psi is positive, yeah. And if psi is negative, if psi is less than 0, right, then the domain is this one. This is the domain of X. And if psi is equal to 0, then the domain is this one. So in summary, you can summarize the domain of X as one of these three intervals, depending on the sign of psi. Okay? Okay, so we talked about it yesterday. And then I explained to you guys how come the GEV combines the three limiting distributions into one. And I showed this once again by considering the three cases. So in the case psi is positive, it can be shown that the formula for the GEV is the same type as the Frechet distributions. I remember this one. This is the Frechet CDF of the Frechet distribution, right? Okay. And if psi is negative, if psi is less than 0, then the formula for the GEV is of the same type as this one, which is the CDF of the Weibull limit. Okay. Okay. And finally, if psi is equal to 0, then the CDF of the GEV is the same type as this one, which is the Gumpel CDF, right? So therefore, the GEV distribution combines the three limiting distributions into one formula. All right? Is that clear, guys? So any questions on what we did yesterday? You can ask me now before I go further. So this is what we did yesterday. Okay. Yeah. The next thing I'm going to talk about is the following. I'm going to put my glass now. The next thing I'm going to talk about is the PDF, or the probability density function of a GV distribution. Right? The probability density function is, I'm going to denote it by little g of x, which is the derivative of capital G of x, right? Okay, so you should differentiate the GV distribution, which is given by this formula here. This is the formula for the CDF. So you should differentiate this with respect to x. What would you get, guys? You will get the following. Alright, this is the, so you see how I got this. This is the derivative of the CDF with respect to x. So therefore this is the density function, or the probability density function of x. Okay? Alright, guys. The next one is quantile. Do you guys know what a quantile is? You must have done this in first year. Yes? What is a quantile? Huh? Are you okay, ma'am? You have a question or what? You okay? Yeah. This is product sign. This dot here means a product. Okay. A quantile, all right. Okay. I mean, a quantile, sorry, can you see? Sorry. A quantile of a random variable is defined by, it's a solution of this equation for xp, right? So I use the notation x sub p to denote a quantile, right? So in other words, it's the value for which the probability that x is less than equal to this is equal to p, right? Okay. So the GEV distribution, right? Okay. So for the GEV distribution, we know that the CDF G is given by this, so this must be equal to P. So now what I'm gonna do is I'm gonna solve this equation. I'm gonna solve this equation for P, for x of P. I mean x of P, right? So it's gonna become, I'm gonna do it slowly so that you can see what I'm doing. Right? Then it's equal to this, yeah. Can you see this? Sorry. Okay, and this. Okay, it's equal to this. Okay, and finally, all right. So this is the Pith Quantile. Oh. All right. So this is the Pith Quantile of the GEV distribution. Right. Okay, guys. Do you follow what I've done? So all you have to find the quantile of a distribution, all you have to do is just set the CDF equal to P and solve for x, and that's what I have done here. Right? So this formula gives you the Pith quantile of the GEV distribution. So in particular, the median I'm sure you know what a median is. What does a median mean? Median is exactly the halfway between. Median is exactly halfway. So P is what? P is half, right? So in this case, P is half. So it will be yeah. So you see, do you see why this is equal to this? Because if you put P equal to half, minus log of p will be log of 2, right? Okay, so the median is given by this formula. Okay, all right. Okay, yes. All right. Let's put it here. The next thing I'm going to talk about is something known as return level. I'm not sure whether you know this before. I don't know whether you heard about this term before, return level. Return level is usually used in like very rare events, like something like stock market. If a stock market crash is going to happen, say 1 in 10 years, right? The return level, the probability corresponding to that will be 1 minus 1 over 10, right? Okay, because you should go back to, all right, let me show you. Let me go back to the picture I showed you a long time ago. Trying to find it, where it is. Not this one. You know the picture I showed you a long time ago about the it's not here. Maybe it's here. Don't know. You know the picture that what I mean, like the picture of the extreme bodily definition. It's here. Okay. Do you remember this picture here? This is definition. I mean, we are still talking about definition 1 of extreme bodily, right? So according to definition 1, there's only one extreme value for every year. This is 1 year, okay? 0 to 1 to 365, 1 year. So there's only one extreme value every year, right? So for example, so if a stock market is going to crash, say every 10 years, right? So you're looking at 10 extreme values, right? You've got so one extreme value for every year. So over 10-year period, you have 10 extreme values, right? So the probability that it will occur every 10 years will be with probability 1 minus 1 over 10. Do you guys follow that or no? No? Come on. Like, okay, let me explain this again. Right. All right, let me write it down, okay? Maybe after I write it down, I will try to explain, okay? So the key word here is the return level with period t, right? So a return level period t is in the units of years, right? So t could be 10, 100, 1,000, 10,000, etc. A return level period t is the level expected to occur. This is occur, right? Occur on average every t years, right? So for example, it could be the stock market crash that is expected to occur 1 in 10 years, or 1 in 100 years, or 1 in 1,000 years, right? Okay, so okay, let xt denote the return level with period t, right? Then the probability that x is less than equal to x t will be what? This is the question I'm asking you, right? If just think very carefully. If you have a value that occurs only on average every t years, right? What would be the probability that x is less than equal to this? Come on, guys. This would be this, right? Or not? And can you see why it is? No? Come on, guys. Why can't you see that? Why can't you see that this must be equal to this? By definition, and the definition is this. This is the definition of return level. It's the level expected to occur on average every t years, right? So by that definition, the probability that x less than x could be the stock value, right? Less than equal to this is right. Okay. Another way of writing is like this. Maybe this would make sense. The probability that x is greater than does this make sense? Because the stock market crash is so extreme. So this is the stock value during the crash, right? This guy here is the stock value during the crash, say in every 10 years. So the probability that the stock value will exceed that is 1 in 10 years, or 1 in 100 years. Does it make sense now? Yes? Okay, I mean these two definitions are the same, of course. Yeah. Do you understand, guys? Because the stock market crash, I mean, when it occurs, is so extreme. The stock value will be like too big, really, really big, right? That is, and the probability that x will exceed that will be 1 in 10 or 1 in 100 or 1 in 1,000 maybe. So this is the definition of extreme. All right. So what I'm trying to say is, here in this slide, we worked out the formula here. This is the formula. This is the formula for the Pith quantile, right? So therefore, xt is equal to, using this formula here, right, is equal to mu right? Okay, so So this is the formula for the return level with period t. So remember always, the return level with period t is the value that is expected to occur on average every t years, right? And the formula for that is this one here, right? Okay. All right. So that's return level, right? Let me know if you still have problems. Okay. The next thing I want to talk about is estimation. Right, estimation. Now, so far we talked about all this distribution, the PDF, the quantile, and the return level. But none of that is going to work if you cannot estimate the parameters. Remember, there are three parameters. The GV has three parameters: mu, sigma, and psi. So without estimating the three parameters, in practice we cannot do anything. So, okay, suppose just a minute. This means I D. Okay. Right. So in this case, when I say you have data on X, so each of the X's here will correspond to the largest value of over a year, right? So for example, X1 here would be the largest stock return or log return on year 2000. X2 will be the largest stock return on year 2001, and so on. Okay, so the most I'm sure all of you know. I mean, I know some of you here have done statistical methods, but if you, the new MSc students, I'm sure you must have heard about maximum likelihood, right? You know what it means, yeah. So maximum likelihood is the most popular method for estimation for any parametric distribution. So basically, it involves the first thing you must do is to write down the likelihood function. Because we have three parameters, the likelihood will be a function of the three parameters. Okay, so it will be the product you guys did this last year, right? And statistical methods. Yeah. Don't tell me you don't remember. Yeah. Okay, it's the product of the PDF of X, which is this one. So alright. So this is the likelihood function. Remember, the likelihood function is always defined as the product of the density function over the data. Alright. Now you can simplify this. If you simplify this, you get the following. Alright, this is the simplified form of the likelihood function. The next step. What is the next step? Right, can somebody tell me? In ML estimation, what is the next thing to do? Huh?
Take log.
Take log. Yeah, good. So you take the log of the likelihood function. Because often it's easier to maximize the log likelihood than the likelihood itself. I mean, the idea of maximum likelihood estimation is to maximize the likelihood with respect to the three parameters. But often it's easier to maximize the log likelihood than the likelihood, right? So you take the log. So all right. So this is the log likelihood function. Then the MLE stands for obviously maximum likelihood estimators of All right. So the MLEs of the three parameters are the solutions of these three equations. So you have to find the partial derivatives of the log likelihood with respect to mu, with respect to sigma, and with respect to psi. And then set them to 0 and solve. Now what I have done here is to, well, let me put this here. I have done some calculations. Hopefully you can see this. These I have done I don't want to waste time in the class, so I computed the partial derivatives with respect to mu, with respect to sigma, and with respect to psi. So this is what you get, right? Okay. And then you set each of these to 0. So if I call this equation 1, call this equation 2, call this equation 3, right? Then send the MLEs of so the MLEs of the parameters, three parameters, are the solutions of equations 1, 2, and 3. Okay, and because it's really complicated, you can't do it analytically. So you have to do this solution numerically. Fortunately, there is how many of you use R? You know the R software. You guys use it? Yes. Some people don't like it. I don't know. Anyway, there is a command in R that can actually solve this for you. The FG there's a command called FGV, right? The FGV command in R right? So if you have a data set, so there's no need for you to write a computer program to do this. So all you have to do is just use this command. And if you have a data set, say on the most extreme values for the last 100 years of a stock market, right? Then you can use this program in R to compute the estimates for mu, sigma, and psi. It's easy, right? So you don't need to write any program to do it, or just plug in the data and you get the estimates for mu, the three parameters, mu, sigma, and psi. Okay, guys, so that's all right. So we have 20 minutes left, but the next topic, all right, I'm not going to do that today, but I will introduce you to the next topic. So far, everything we talked about so far is for definition 1. But you may remember last week I told you there are 3 definitions for extreme values, right? There's definition 1, definition 2, and definition 3. So the next thing we will talk about is definition 2. I'm not going to start it today, but because it will take time, right? And then after definition 2, we will do definition 3, right? Okay. So, but what I'm going to do in the meantime, just to prepare you for the example class today. This is the example class. Do you guys, did you try these questions? I asked you to try them. Did you? Which one had you done, or which one you haven't done? All of them? No? No. I mean, the thing is, some of these questions are difficult, really. Some of these questions are really difficult. Some of them are easy. But I want to show you how to do one of the difficult problems, because I will show you now how to do. This is question 11. Question 11, sheet 1, right? Do you guys have copies of this? Everybody has a copy of this? You have it? You don't have? Oh, you have it, right? Okay. So if you look at question 11, it says, it's this one here. It says you have a class of distributions defined by this, right? Show that F belongs to the same max domain as G. You may assume these are equal. Now what that means is the following. You see, there are three possible max domain F can belong to: the Frechet domain, or the Gumbel domain, the Frechet domain, or the Weibel domain, right? So when I say F belongs to the same max domain of attraction as G, it means the following. It means right? So it means that you need to show three things. So I will call this A, I will call this B, and I will call this C. So this question, it comes up in every exam paper. So it contains three parts. The first part is to assume that G belongs to the Gumbel-Max domain, and show that F also belongs to the Gumbel-Max domain. And the second part is to assume that G belongs to the Frechet-Max domain, and show that F also belongs to the same. And part C is assume that G belongs to the Weibel-Max domain, and show that F also belongs to the same. Right? Right. So for example, I don't know if I have time, but I will show you how to do the part A, but part B and C are similar if I have time. So part A, okay, assume G belongs to the Gumbel-Max domain. Okay. Right. Okay, then by condition 1, we know that there exists a positive function gamma t such that this is true, right? Okay. Now, let me call this star, right? Okay, now I'm going to show you that F also belongs to the Gumbel-Max domain. So I will start with I will start with this, right? And I will show you in a few minutes that this guy here is equal to E of minus x, or something similar to that, right? By the way, there's no need to copy this down unless you really want to, because you should. Do you guys look at my website after the lectures? You do. So I put the scan notes and also the podcast immediately after the lectures. Yeah. So now this here, guys, is equal to Do you know what I have done? from this to this? What have I done? Can you tell me? What have I done? Where's my pen? Come on, guys. How did I get from this to this? Lopital's rule, right? So you remember the Lopital's rule. If Lopital's rule says the following, that if you have two functions, say alpha beta, all right? No, not alpha beta, maybe something like f1, f2, okay? Say you have a ratio of two functions, say f1, f2, and you're taking the limit, right, as x goes to something, right? This is the same as the limit this is the same as the limit of the ratio of the derivatives, right? If right? So this is known as the I don't know whether do you guys remember this or not? This is known as the Lopital's rule, which says that if the limit of both functions, right, is equal to either 0 or plus or minus infinity, then the limit of this ratio is the same as the limit of the derivatives, the ratio of the derivatives. You know this result, right? Okay, so that's what I have used. I have used from this line to this line. I've taken the derivative of this with respect to t and derivative of this with respect to t, right? Okay, and then we still have time.